calculate the osmotic pressure of a solution when 5 milligrams of aspirin which is C9H8O3 is dissolved in 250 milliliters of water at 25 degrees Celsius. So I'm going to give y'all a second to work that. What are you going to have to do? You've got to find molarity. Okay, so I'll give y'all a second to work on that. Okay, so since we're looking for molarity, y'all know that you've got to take the 5 milligrams of aspirin and convert that to moles, which is what you're working on, right? 5 milligrams is 0.005 grams, isn't it? And the molar mass that we all got is 164.17 grams for molar mass. Agree? And when I converted that to moles, I got 3.046 times 10 to the minus 5 moles. That's what y'all got? Okay. That's how many moles of aspirin. Can I keep going? Or? Alrighty. How do I get molarity? What do I do with that number? I divide that by 0.25 liters because molarity is per liter. So I take this number, divide it by 0.250 liters, and for my molarity, I have 1.22 times 10 to the minus 4. Is that what y'all have? 1.22? 1.22 times 10 to the minus 4 molar. How about it? No, is that okay for molarity? Okay, yeah, that's what I'll do. I'll leave everything in my calculator and keep it there. So that's all I was lacking in order to plug into osmotic pressure. The osmotic pressure is molarity, 1.22 times 10 to the minus 4 molar. Times the ideal gas constant, 0.0821 liters times atmospheres per mole times Kelvin. Times temperature, which is what? 298 Kelvin. And I got for an osmotic pressure 2.98 times 10 to the minus 3. Is that what y'all have? It wouldn't matter. What do you mean? That's what y'all got. Y'all got the same number I have.
Yeah, she put
2.98 times 10 to the minus 3.
Yeah. Okay.
Yeah.
Can we leave it?
Oh, yeah. It doesn't matter if you put a decimal or put it in scientific notation. I don't like to write 0.00298. What are the units on that? The units on that are atmospheres. That's that answer. That is the answer for this one. But remember, Monday we talked about Van Hoff factor. Does this one have a Van Hoff factor? No, because it's molecular. Because it's aspirin. Look at aspirin. C, H, and O. That is a molecular compound. So technically it has a Van Hoff, but the Van Hoff would be 1. Right? If it had not been a molecular compound, if it had been, say, what would have a Van Hoff? You can't pick something I gave an example of on Monday. Pick something different that would have a Van Hoff factor. Lithium chloride. Why'd you pick that? Because it's an ionic compound. Had we dealt with something that was an electrolyte or was a strong acid, then when we got to this final answer, we would have multiplied it by whatever that Van Hoff was, by 2 or by 3 or by 4. Okay? But this one did not have a Van Hoff factor, so we were fine. Now, go in your books to page 564, please. Page 564, kind of at the top of the page, kind of in the middle, I guess. There's a practice problem A. If you don't have a book, then ask your neighbor if you can look on with them, because I'm not going to rewrite the problem on the board. Practice problem A says a solution made by dissolving 25 milligrams of insulin in 5 mils of water. Do y'all see that? Practice problem A on the middle. Page 564. Yeah, that practice A, a solution made by dissolving 25 milligrams. Y'all see where I am? Okay, good. Work that one. We worked some like this on Monday. Okay, you know that molarity in the formula, MRT, you know that molarity is moles of insulin per liter of solution. Do you know how many moles of insulin you have? No. You know you've got 25 milligrams of insulin, right? But you don't know what the formula is, so you don't know how many moles that is. Do you know the volume of your solution? Yes, you know the volume of your solution. So do you guys see that when you take that molarity and break it down into moles of insulin per liter of solution, moles of insulin is what you're going to be solving for in this problem? Like we did on Monday? No or yes? Or I don't know. Huh? No, you don't know molarity, but you know that this is what molarity is, moles of insulin per liter of solution. The liter of solution you know, right? It's 0.0050. Huh? Okay, let me go over here to my next slide, and let's start plugging numbers in, okay? Pressure is 0.02039. I don't know what M is, but I know it's however many moles X over 0.005 liters. I know what R is, right? And I know what T is. And so what I can solve for is X, which is moles of insulin. So solve for X. Do you guys have X? If you're doing it...
You multiply that by?
Just solve for X. How do you solve for X, y'all? Yeah, you got to cross multiply and then divide. That's what I did.
What'd you do? I think you get one.
Do y'all get that?
Wouldn't it be 4.169?
Not mine. 4.165. Okay. Okay, set up like I have it. I said 0.02039 times 0.005, right? Cross multiply. And then I've got, to get X by itself, I've got to divide that number by the product of 0.0821 and 298. And when I do that, I get X is 4.168 times 10 to the minus 6 moles of insulin. The question's asking for what? Molar mass. No. What's the units for molar mass? Y'all, this is just like the problems we did Monday. It's just on Monday, y'all used the boiling point elevation and the freezing point problems. Molar mass is grams per mole. Do we have a grams of insulin? Yes. The problem told us it was 25 milligrams, so we know that that's 0.025 grams, right? And now we know how many moles of insulin that is. So we simply say, for the molar mass, 0.025 divided by the 4.168 times 10 to the minus 6. And you have the molar mass of insulin, which is probably going to be a big number.
5,995.2.
5,998 grams per mole. Y'all just aren't used to seeing things like that, but molar masses can be big. Insulin's not small, obviously. It's a big molecule, big hormone.